we have been discussing various components which are used in optical communication system. We saw that for a wavelength division multiplex system, we require variety of components, and last time we investigated one of the components, which was the optical amplifier. So, we have seen that we require a background technology for WDM systems, and that is we require optical amplifiers, we require switches and couplers, we require fiber Bragg grating devices and so on. And last two lectures essentially we investigated the optical amplifiers, and in detail we saw one of the amplifiers, what is called the EDFA. We saw that if we take the normal fiber and dope the core of this fiber with erbium, then we create the energy levels such that we can amplify the light in the wavelength band of 1550 nanometer. So, typically we get a bandwidth of about 30 nanometer in that band. So, about 30 to 40 WDM channels can be amplified in one shot by using this device. The second class of devices which we require for WDM networks are switches and couplers. They fall in the category of integrated optical devices. So, in fact, as the name suggests, these are the devices which are fabricated on a wafer. So, you are essentially creating the light guiding environment on some substrate. So, the circuit essentially looks like an integrated circuit, and that is how you do get the name of integrated optical devices. So, you are creating certain wave guiding structures on the substrate. The signals which come from the optical fiber is connected to this device. The properties of the light are changed, and then the light is again launched back on the optical fiber. At the heart of this integrated optical devices, we have a phenomena what is called the electro-optic effect. So, we have certain materials whose dielectric constant can be changed by application of electric or magnetic fields. So, if you consider a material which changes the dielectric constant when an electric field is applied across that, these materials are called the electro-optic materials, whereas if the properties are changed by application of the magnetic field, then we call those materials are the magneto-optic materials. Here we predominantly make use of the material which is electro-optic, and the effect that the dielectric constant of the material changes by application of the electric field is called the electro-optic effect. So, this effect essentially means that the refractive index or the dielectric constant of the material changes with application of the electric field. And there are two materials which have been studied in great detail. One is what is called lithium niobate, and other one is the gallium arsenide. The lithium niobate is a rather lossy material, but it gives the change in dielectric constant or refractive index relatively large. That is the reason large number of electro-optic devices are based on the lithium niobate material. Other material which is gallium arsenide, it requires relatively high electric fields to realize the same change in the dielectric constant, but this material has less loss, but it also has the low what is called the electro-optic coefficient. So, we essentially will talk about the devices which are based on the material which is the lithium niobate material. So, basically if you consider this material is an anisotropic material. So, the refractive index or dielectric constant in different directions, and when the electric field is applied, the dielectric constant change depends upon which direction the electric field is applied with respect to the axis of the crystal. So, without going into that detail, in short we can say that we have a material, the refractive index of which can be changed by application of electric field, and the change in refractive index delta n is equal to n cube by 2, where n is the refractive index of the material, or this quantity is called the electro-optic coefficient, which is a material property, and E is the applied electric field. This is also called the Pocal effect, that the refractive index is changing proportional to the electric field. So, now by using this property of the material, we essentially can alter the characteristics of the light when the light passes through this material. So, basic device which is fabricated by using this is what is called a phase modulator, and the device is as follows. Let us say we have a substrate here which is lithium niobate, and then we do some doping of this. So, a channel waveguide is created inside this wafer. So, let me just show how 3-dimensionally it will look like. So, if you have a lithium niobate substrate which is like this, by doing some ion implantation or something, we can dope this. So, if you look in 3 dimension, essentially we have created a semi cylindrical kind of structure, where refractive index of this region here along the length is relatively higher compared to the refractive index of this substrate. So, if you imagine like we had an optical fiber, and if we cut this optical fiber along the axis like half, that is the kind of structure essentially we have created here. So, here we have a refractive index of lithium niobate, here we have a refractive index which is little higher than the refractive index of lithium niobate, and above this we have air which has a refractive index 1. So, essentially this structure is capable of guiding light along this, because you have a higher refractive index in this region. So, though the structure is not symmetric in the cross section, but in principle light can be guided inside this, because this structure is similar to optical fiber, where core has a higher refractive index surrounded by a low refractive index material. And that's what essentially is shown here, that you have a substrate and you create this thing here, what is called a channel waveguide. So, this thing we call as the channel waveguide. So, now what we do, we bring the optical fiber from this, connect to this. So, the light is brought from the optical fiber connected to this end, then on the other end of this device you collect the light from here, and the light will pass through this material, and because of that the phase of the light will change. And how much phase the light will change, that will depend upon the length of this channel waveguide, and will also depend upon the phase constant of light inside this waveguiding structure. So, once this device is fabricated, you have a fixed change of phase between the input of the light and the output of the light. What we want essentially is that a mechanism by which the phase of the light can be differentially changed by application of certain signals to this device, and that's where we want to make use of this effect, what is called the electro-optic effect. So, now let us say that around this channel waveguide, suppose we deposit some conducting layers and apply certain voltage to that. That voltage will create some electric field. That electric field will pass through this, and that electric field will change the refractive index of this material. If the refractive index changes, the phase constant of the light will change, and therefore we will have an additional phase change because of the change in the refractive index. So now you get the change in the phase of the light here, depending upon whether the field was present or field was not present. And that's what precisely is shown here, that you have this channel waveguide, and these are the metal coatings, what I call the electrodes. The light is input from this side, which is continuous wave. Light passes through this, and now we are applying now a signal to the electrodes, let us say in the form of some square wave. So when the voltage is applied, the refractive index of the material will change, and because of that the phase of light will change. So you will have essentially two phase values of the light, one corresponding to this voltage, other correspond to this voltage. And if this voltage is 0, then we say this will correspond to no electric field, whereas this will correspond to when the electric field is present. And consequently you will get the change in the light phase in the output. So we will get what is called the phase shift keyed signal at the output of this device. That is the principle of the phase modulator. So what we are doing, essentially we are changing the phase of the light which is coming out from this device in accordance with the amplitude or voltage applied to the electrodes of this device. So now one can write the phase change which is going to take place because of this application. So let us say now I have a phase change delta phi, that is equal to the phase constant in free space, which is 2 pi by lambda, where lambda is the wavelength of the light, into change in refractive index, which is delta n, into the length of the channel waveguide. And as we have already seen, this quantity change in refractive index is given by n cube by 2 into r into E. So we can substitute into this. So you get change in the phase, which is 2 pi by lambda into n cube by 2 into r, which is the electro-optic coefficient, into the electric field, into the length of the device. For a given device and for a given optical signal, lambda is constant, n is constant, the refractive index of the substrate material. The electro-optic coefficient, which is the material property, is constant. So essentially we have only the product of this E and L. That is the thing which one can vary when one designs this phase modulator. So if you have the high value of the electric field, then essentially we can have very small dimension. The length required for this device may be reasonably small. But what one can note is that this quantity, which is change in refractive index, which you have here, is generally very, very small. So when you apply the electric field for changing the refractive index of the material, the change in refractive index typically is of the order of 10 to the power minus 6. So what that means is that to get a substantial phase change into the light, signal, we require a significant length for propagation of light. So, it is then immediately clear that since this quantity delta n is very, very small, you require a length which is typically of the order of about few millimeters to get a significant phase change in the light output. Also, we have to create certain mechanisms by which the electric field is large for the typical voltages which you can apply to these devices. So, let us say we are going to apply the signals typically of the order of about 10 to 15 volts. This V voltage is practically in the range of 10 to 15 volts. Then the electric field can be enhanced by essentially decreasing the separation between these electrodes. So, bringing the electrodes close to each other, the electric field can be enhanced and consequently the size of the device can be reduced. Nevertheless, the size of the device cannot be miniaturized to a great extent, and you will require at least few millimeter length for interaction to get a substantial phase change in the device. If we now want to create a signal here which is binary phase shift keyed signal, that means we want the phase change in the output corresponding to two levels, one 0 phase and one pi phase. One can essentially ask what is the voltage required to get the phase change which is equal to pi. So, let us say if the voltage difference between these two electrodes was V and the separation between them is D, the electric field can be approximately V by D. So, we can write this here, this is 2 pi by lambda n cube by 2 R electro-optic coefficient V by D into L. So, one can then ask what is the voltage V pi voltage which we will get, which will give me the phase change of pi. So, when I apply no voltage, this delta phi is equal to 0. So, I can say that corresponds to my reference phase. When I apply voltage V, the phase must change by pi. So, let us say I call that voltage as V pi. So, for delta phi equal to pi, we get V is equal to V pi. We can substitute into this and we get the V pi voltage which is equal to lambda upon n cube R to D upon L. So, as I mentioned, since to get this value, this we put equal to pi, delta phi equal to pi. So, now I require a substantial L to get the corresponding value of V. And as I mentioned, this V value should lie in the range of about 10 to 15 volts, TTL kind of signals. D also cannot be reduced significantly for the simple reason that if we try to reduce D, then the electric field is going to be partly inside, partly outside, and then the field strength might become larger than the breakdown fields, and then you may have a sparking between this. So, the separation between the electrodes cannot be more than few microns, maybe more than that. So, essentially the D cannot be arbitrarily decreased to get the value of V pi. So, we see that there is a limitation of all these quantities here, we cannot reduce D significantly, and that is the reason essentially one will require the substantial length to get the V pi voltage reasonably low. So, this is the basic now module which we have, which works on the principle of electro-optic effect, and the phase of the light can be changed by application of the signal voltages across the channel waveguides. As the frequency of this signal increases, there are certain implementation problems for this. One is, if you have the electrodes which are of few millimeter size here, you have a substantial capacitance which is going to be there between these two, and when you connect this signal which is coming from some source, it has some internal resistance, impedance, and that resistance combined with this capacitance essentially has a time constant, and therefore this voltage cannot be switched at a very high speed because you have a RC time constant associated with this system. So you have a switching speed limitation for this. The improvement of this could be that one can treat this structure like a traveling wave structure. So one can have a situation where these are the electrodes, and these electrodes can be treated like a transmission line, and then you have a channel waveguide in which the light is traveling. So we can connect a signal between these, which is the signal which you want to apply, the voltage. And since we are having this voltage at reasonably high frequency, like few gigahertz, there will be a signal traveling on the structure with phase velocity, and the light will be traveling inside this in the channel waveguide. So now if I look at the structure edge on, essentially the structure looks like this. We have these electrodes which are here, where the voltage wave is going to travel, and we have a channel waveguide which is here where light is going to travel. So here is the light, and here is the voltage or E field. So since now the radio frequency or the signal frequency is much lower, it is typically in the range of, let us say, a few gigahertz, you have a substantial field lying outside the substrate, whereas the light is more or less confined inside this region. So as a result, what happens is the refractive index seen by the wave corresponding to this voltage is different than what refractive index the light sees, and consequently the phase velocity of the light signal inside the channel waveguide is quite different than the phase velocity of the voltage wave which is going to travel on the structure. So we have what is called a velocity mismatch between the optical signal and the modulating signal, radio signal, which is going to modulate this light. So if there is a velocity mismatch for a certain portion of light, you will see that for some time the signal voltage is positive, both are traveling together, but now since they are not traveling with the same speed, sometimes you will see positive voltage and negative voltage here interacting with that light. After some time, when the light has moved to this location, there is a difference in phase, so here this becomes positive, this becomes negative, so phase is reversed. So ideal situation, as we increase this length, the phase would have accumulated, it would have increased linearly as a function of length, but now we see that does not happen because the voltage signal which travels on the electrodes has different phase velocity than the phase velocity of the light which is confined inside the substrate. So one then has to do some innovative ways to create the structure so that the electric field and the light both see the same refractive index, and therefore they travel with the same velocity, and you get a better velocity match so that you get effective accumulation of the phase change, and then with a small length you will be able to get the desired phase shift. So these are certain practical aspects which are there in the design of the phase modulator. Once you have created the phase modulator, then we can essentially build around this now. So what it appears is that by using the electro-optic material, changing the phase of the light is the simplest thing. But once the phase of the light is changed, then we can create some kind of a interfering mechanism so that the change in phase can be converted into change in amplitude. So though in principle we are having a device which generates the phase shift keying, we can convert the phase shift keying device into the corresponding amplitude shift keying device, or a device which can give you intensity modulation for the light. And that device is what is called the Magenta Interferometer. So idea here is very simple. Essentially, as the name suggests, you have an interferometer here. So you take the light, let the light go by two paths. One of the path is like a phase modulator. You change the phase. When the light is combined back, you have interference, and depending upon how much phase the light has gone in one of the arms, you will get the corresponding light output. So a basic Magenta interferometer structure is as follows. You have the light coming in, you divide this light into two parts. It goes by two arms. You combine this light back in this and you get the output. This is the device which is what is called the Magenta Interferometer. So what we are showing you here, we are showing here the plan on the lithium niobate. One of the things on here is like a phase modulator. So you are having a substrate here which is lithium niobate, and on the lithium niobate you have created now the channel waveguiding structure which will look like that. So the light is brought here, you have a two-way power divider. So the light gets equally divided into these two parts. It propagates in these two arms, and again it combines here with equal combiner, and you got the light out. Assuming that these two are exactly identical paths, when the light reaches here, it will reach in phase, and therefore whatever signal you are giving here, the whole signal will appear at this point. Let us now say that we put the electrodes around this. So we have created a phase modulator around one of the arms of this Magenta interferometer. So we apply a voltage which is this. So let us say this is voltage which is V. So we are applying here now a voltage which goes like that. This is 0, whereas this voltage is V pi. So when the 0 voltage is applied, these two arms are exactly identical, and then the light coming from this path and this path undergoes the same phase change. So you see the constructive interference of light, and we get the light output. Whereas when this voltage is V pi, that time this light will undergo a phase change of pi, and therefore the light reaching from this arm and this arm will be 180 degree out of phase. So we will have destructive interference of light, and we will not see any light coming out of this. So we will get a 0 light. So if we have now the light, continuous light here, CW light, whenever we have a one level here which represents V pi, that time we will get the light output which will be 0. And whenever we have no voltage applied which corresponds to 0, we will get the constructive interference and we will get light intensity like that. So, if this was you transmitted a signal 1 and 0, then the output we will get essentially complement of that. There will be no light here, this will be 0, this will be 1. So, essentially we will get here the intensity modulation of the light with inversion. So, whenever the signal was 1, that time we get no light intensity. So, we have essentially inversion which has taken place in this device, but otherwise the amplitude modulation characteristics of the signal are transmitted to the optical signal. So, you got light here which is intensity modulated. So, what we are seeing now is that using the basic device which is this, we can build on this and then we can build the amplitude modulators. So, by using the Magenta Interferometer geometry, we can create the amplitude shift keying or intensity modulation. So, in those applications when we go for the high speed transmission, normally we do not modulate the lasers directly. We have seen earlier that if you are using the low data rates, by changing the current of these devices, the light intensity can be appropriately changed. So, when we talked about LED or when we talked about lasers, we saw that by changing the current of the laser or the LED, we can create the intensity modulation. However, that direct modulation is good when you are having the switching times which are long or when the data rates are not very high. If the data rates are very high, then directly switching the currents for the lasers on and off create deviation of the frequencies, which is not very good. So, normally what we should do is, we should do the way normally the electrical engineers would do. In electrical engineering, when we create a modulation system, we never modulate the oscillators directly. We have an oscillator which generates a continuous wave, then we give this continuous wave to a modulator, where the modulating signal and what is called a carrier or the continuous wave are combined together, and then we get the corresponding modulated output. Same thing essentially we have to do now when the data rates are high. So, by using this device, essentially what we are going to do, we have a laser which is continuous. So, we are not switching the laser on and off, so we can avoid all the frequency instabilities which are going to be there. Then we give that continuous signal device to this device here, apply the data. This data is going to change the properties of the light and we will get the corresponding intensity modulation. So, when you go to the high frequency operation, high speed operation, essentially one have to use the external modulators to modulate the characteristics of light, and even the intensity modulation may require a device something like this. You can also create the amplitude modulation by another device which is very powerful, which is what is called the directional coupler. We will have a discussion on that little later. But let us see now that by using this integrated optical effect, electro-optic effect, we have created integrated optical devices which look like the integrated circuits and which can alter the characteristics of light, like it can create the phase modulation or it can create the amplitude modulation. The another component which we require in the WDM system are the couplers. So, essentially you are having a light which is coming from somewhere and you want this light to get coupled to some other device, Or let us say if I have a light which is coming from somewhere and I want to distribute this light to various users, I require essentially a device which is like a power divider. So, light will get divided into multiple paths and it can be distributed to various users. Or I can have n fibers coming, each one is carrying their own optical signals, and I want that all of them should be distributed to all the users which are there on the other side. These kind of operations are carried out by the device what are called the couplers. And there are two types of couplers. One is the simple fiber fuse couplers, which do not have great wavelength characteristics or some selectivity or something like that. And these are essentially used for distribution of light to various destinations. So, here the idea is simple. We have large number of fibers. You simply take the fibers and twist them and fuse them, heat them with some flame, and slowly the cores of this fiber merge into each other, and you have created a common region here where all the signals essentially will be mixed together. So, if the signals are coming at different wavelengths, all wavelengths essentially will get combined into one, and then from this common area again all the wavelengths now will get divided into all the users. So, let us say if I have lambda 1, lambda 2, lambda 3, lambda 4 wavelengths, they all will get combined into this, and each one of the output would have a wavelength lambda 1, lambda 2, lambda 3, lambda 4. So, what this coupler essentially has done it has combined the light which is coming at different wavelengths from different users and distributed each wavelength to each user on the other side. This is what is called a fuse star coupler. Schematically, then one can show this device which will look something like this. You are having a star coupler here, and there are some n channels which are coming in, and the power essentially is distributed to all of them. But now, since the same power is distributed to all the people, each channel essentially would receive 1/nth of a power. So, in fact, there is going to be a limitation of how many fibers you can fuse together, because you will require at least minimum power in each of these channels to get the proper detection of the signal. So, you cannot arbitrarily increase the number of the input output for the star coupler, but the basic operation is same, that you have a set of fiber which are fused together and the light gets combined into this and again get redistributed to all the users. So, in a typical passive distribution network of WDM system, we would need a device which will be like star couplers. The other class of device which is far more powerful than the simple fuse coupler would be what is called the directional coupler. So, we will see that if we take the two fibers and suppose we bring the fibers very close to each other. Now, if you are having the cladding on the fiber core, then just by bringing together or even touching together, nothing great will happen. But suppose we remove the cladding of the fiber, so that now the core get exposed, and consequently the field of the light which is propagating inside their core now extends much outside. Now, if you bring these two together, their fields will start interacting with each other, and that is the basic phenomena we want to exploit. That now, when the two fibers have come close to each other, because of the interaction of the fields on these two fibers, some exchange of power can take place. That is the basic principle of the directional coupler. So in principle, essentially what we are doing is we have these two fibers which are there. We bring very close to each other and then the fields start interacting with each other, and then during this process some exchange of power takes place, and we will see in detail what are the characteristics of this exchange. So we have a coupling region which will decide how much power gets coupled and how much power remains with the same fiber and so on. But essentially by bringing the two optical channels close to each other without actually making physical contact, just by the interaction of the evanescent field which are going to extend outside the cores, we can make the coupling of the power between two optical fibers. So schematically, let us say what we are saying. We are talking about essentially a configuration something like this. This is now like a channel waveguide. So we have a substrate and we have created now the two channel waveguides, one this, which are close to each other. So now we are not talking about optical fibers here, we are talking about integrated optical devices in which there are two channel waveguides which are sitting next to each other, and the optical energy is primarily confined to these channel waveguides, but you have an evanescent field which extends into the substrate. So we have these two waveguides here, A and B, let us say, which are channel waveguides, and we have these fields which are the modal fields corresponding to these two channel waveguides. Let us make the analysis for specific application. So just to make the analysis simple, let us assume that these two channel waveguides are identical. What that means is that the phase constant of these two are identical, the refractive index is identical, width is identical, everything is identical. And then let us say we excite one of these waveguides. So idea here is as follows: we have one channel waveguide, there is another channel waveguide which is next to it, and we excite this waveguide. When we excite this waveguide, it is going to generate the fields. So it will have a modal field distribution which will look like that, and as we have seen theoretically, this field extends up to infinity, which is the evanescent field. So if the second waveguide was not there, then this field will propagate along the structure in this with certain phase velocity. Now let us say we have another identical channel waveguide and we bring close to this waveguide without touching each other, just they are in the proximity of each other. As soon as you try to bring this waveguide close to this field which is extending theoretically up to infinity is now intercepted by this. So obviously this distribution cannot remain like this because now the boundary conditions are changed. So consequently some field will get induced inside this waveguide. But since this waveguide is a guiding structure and is identical to this, any arbitrary field cannot be excited inside this structure. What you can excite inside the structure again is the modal distribution. So essentially the field which can get excited inside this will be the modal distribution, which will be this, which will again extend theoretically up to infinity. Now this field distribution which you have here, this field distribution is created because of this. So if this one is moving with a phase velocity, even this field distribution will start moving. If it starts moving, essentially we have created now a wave which is going to move on this structure. Since the wave is moving on this structure, it will require certain energy, but we have not supplied any energy to this waveguide. We supplied the energy to only this waveguide. So, from where the energy would come? It has to be tapped from this source. So, initially although we excited this waveguide, just because of the coupling through these evanescent fields which are extending much beyond this channel waveguide, the power will get coupled to this waveguide. And not only that, as this remains, the power will go on coupling to this waveguide, and the power on this will go on building, and the power on this one will go on reducing. So, what we find something interesting now, that if you bring the two optical channels in the vicinity of each other, you can have an exchange of power from one channel waveguide to another waveguide. In fact, that will be true even for optical fiber, that if you bring two optical fiber cores very close to each other, there will be transfer of power from one core to another, even if there is no physical contact between the two cores. Now, you recall when we were talking about optical communication, we had said that optical communication is very secure, the information cannot be tapped. But all that is true if the evanescent fields of the optical signal which is going inside the optical fiber is not accessible. If the evanescent field becomes accessible, then you will have a coupling of these fields, and then the information can be tapped. So, inside the optical fiber, when you are having a cladding around the core, normally the field becomes negligibly small by the time you come to the external boundary of the cladding, and that is the reason we do not have coupling of the signal. But if you remove the cladding from the optical fiber, then this field will get exposed, and then these fields can be tapped very easily. So, the basic principle of directional coupler is this, that just by bringing the two channels in the proximity of each other, the evanescent field starts interacting with each other, and because of that you have exchange of power between the two waveguides. Let us now see physically how much exchange would take place between this, and this qualitatively one can argue as follows. So, initially when we started, we have now a structure which looks like that. These are two channel waveguides. Instead of considering these two structures like two waveguides, we can say we have a structure, composite structure, for which the refractive index variation is this. This is what channel waveguide essentially does. You have a refractive index something here N2, you have a refractive index here N1, here it is N2, here it is N1, here it is N2. So, we can consider something like a superstructure which has a refractive index variation something like this, and we have excited only this waveguide. So, we have to start with, let us say at z equal to 0, some location at the input, we have a field distribution which looks like that. That is what we started. Now, what we can do is we can visualize this field distribution as a combination of even and odd function. So, we can say this is equivalent to one structure which is even function and one odd function. So, this is the even function and this is the odd function. So, at z equal to 0, this field distribution can be thought of as two field distribution, superposition of two field distribution, one is even, one is odd. Now, these two field distributions, since they have relative variation of the intensity in different refractive index medium, these two will have different phase velocities. If they have different phase velocities, as they start propagating, the phase difference between them changes. So, if I go to certain value of z, at some Z1 such that the phase difference between these two fields has become 180 degrees. Then at this location the even and odd function would become like this. There is 180 degree phase shift, so this will become so this is the even function and this is the odd function. But now the odd function is gone, phase change of 180 degrees with respect to this. As a result, these two will cancel and these two will add. So what we find is at z equal to 0, the power was here. But if I go to z equal to some z1 where the phase change is pi, the power distribution has become like that. It is here. And there is nothing here. Or in other words, what we are seeing is, if we bring these two channel waveguides together, not only a small power will be tapped from this waveguide to this waveguide. In fact, after a certain distance, the entire power will shift to a second waveguide. So through the evanescent field, the coupling is something which can take away the entire power from the original waveguiding structure. And that is very serious, because now we are saying just by bringing the two waveguides in the proximity of each other, we can take away the entire power from the original waveguide to the second waveguide. But theoretically, that's what would happen if you consider the two waveguides like this. So at a distance where this phase change become pi, the power will go from here to here. Again, if you go a distance of same where the phase change will become 2 pi, again the power will come back to this. So essentially the power is going to now go like this. So it starts from here, slowly the power gets transferred to this waveguide, slowly the power gets transferred back to this waveguide, and so on. That is the principle of the directional coupler. So when we meet in the next lecture, we will write down analytical equations for this simple device, directional coupler, under the assumptions that the two waveguides are identical, and then from there we essentially develop the quantitative expressions for how the power is going to vary from one waveguide to another waveguide as a function of length, and then we will see how can we make more innovative devices by using this device, which is the basic directional coupler.